We have Professor Jurg Keller, who is the Director of the Advanced Water Management Centre at the University of Queensland since its inception in 1996. He's a Professor in the School of Chemical Engineering and an ARC Professorial Fellow. He was elected to the Academy in 2011, and he was a member of the Steering Committee, so he has been intimately involved. Thank you, Eric.
Peter, and thanks everyone for turning up. It's quite impressive to actually see the interest and the level of people that are actually coming to this, even though I think we're talking largely to the converted, but hopefully we'll get a few more getting the message out there. So I was trying to put together a bit of a summary of what is the advanced water treatment, because it plays a key role in when we're talking about recycling, and not just in recycling, but certainly in the recycling context. I've put these definitions together, so they're not out of somewhere Google or wherever, but they're actually my own words. And I think it's key that we understand that advanced water treatment is sort of two parts. One is a process technology part, so there's a multi-barrier process with complementary technologies and so on, and they provide a particular level of purification, basically from quality compromised sources, I call it that. It's not just recycling, there is actually some of the people in Europe, in Netherlands for example, they're making drinking water out of pretty crappy raw water, to be blunt. But they can actually do that as well. And in some ways, they're actually using advanced water treatment rather than just the traditional ways. But then more importantly, it's not just the technology, it's the technology plus an operating system, staff, the whole monitoring and control system that's behind it that makes sure that this actual technology works as best possible at any one time, and we know it is actually achieving what it ought to be achieving. So I think it's two key parts that we really need to keep in mind. So just to give a bit of an idea, and probably most of you have a pretty good idea what we're talking about, I think we have to acknowledge though that we're actually looking at advanced water treatment, so it goes beyond a very good, well-performing biological wastewater treatment plant. So we're already using them anyway because we've installed them for environmental protection. But that's a key part. We're not talking raw sewage going into these processes. They're actually already quite well treated. It uses then a multi-barrier process with physical and chemical treatments usually. So you can see already we have biological in the wastewater treatment. We have physical and chemical processes that actually work in conjunction. We get a recovery of maybe 80-85% typically in these situations, so it's not 100%. There is an outlet for basically the things you cannot destroy. So we can destroy certain organics or whatever, but certain things which you simply cannot completely convert into CO2 and water, so we have to have an outlet, so it's not all of it is 100% recycled. And the energy input is around about 1 kilowatt hour per cubic meter. Now, I know a lot of people think, oh, yeah, what's a kilowatt hour? Well, typical households are 20 to 30 kilowatt hours per day water consumption. Or if you turn this around, with that energy that you can make a whole ton of water, we're talking a ton of water, 1,000 liters of water, you could have about a 5-minute shower. That's not the water, that's the energy to heat up the water to have a 5-minute shower. That's equivalent to make a whole cubic meter, a whole ton of that water of very high quality with these sort of systems. So it's not really outrageously sort of energy intensive and whatever. Sure, it uses more than the traditional water supplies, but they're extremely efficient actually in many ways, and to some degree we're using obviously gravity and rainfall and so on as part of the process. The key processes that typically are involved, and I mean this is not to say that's the only way to do it, but quite often we have the wastewater treatment, then the pre-treatment with some coagulants usually, microfiltration and RO, dual membrane systems or ultrafiltration RO, and then there is a further oxidation type process, a chemical process with, in this case, UV peroxide, for example, in case of the installations in Queensland, plus chlorination as a further barrier, and occasionally there is ozone or other treatment processes in line as well. Just to give you a bit of a feel, not maybe everyone has been on a wastewater treatment plant or an AWT, TP. That's a wastewater treatment plant. It's one of our nice ones in Brisbane. And that's a key part of it. When you look what comes into a wastewater treatment plant and what actually goes out in the final clarifier, and that's what the clarifiers look like, it's amazing actually what you achieve. Now, I'm not going to advocate you go and drink what comes out, even though it looks quite nice already. But that's quite an important step in the whole process. Then we go into the pre-treatment. It's not usually you can see a lot other than big pipes and tanks and things. Then you have a microfiltration stage, which is all these vertical modules that most typically used in hollow fiber systems in this case. Then you have a key part, which is the reverse osmosis, which is exactly what is used in seawater desalination as well. And you can get a bit of an illustration of the size of these things. And they're really quite crucial processes. And then you have the further advanced oxidation process, which is a chemical process quite often used in these situations as well. So that sort of gives you the process, and it's actually an example, not even from the domestic plant, but that's actually from an industrial one. I'll talk in a minute. And you can sort of, it's hard to see sometimes, but you can see a little bit that there is still, this is the microfiltration feed, so there's already been pre-filtered in a sand filter in this case. There's a bit of color, there's a bit of turbidity still there. What comes out is absolutely sparkling, crystal clear, and there's no color in it at all. And actually, when you look at the concentrate side from the RO, you can see where the color is gone, because that's quite colored indeed. Okay, so where are these things used? Obviously, indirect potable reuse schemes, nationally and internationally, and Ian Law is going to mention some of the schemes, the direct ones or the indirect ones. The ones we've been building in Australia as well, like in Brisbane, for example, they use exactly that sort of process. But it's also used for potable water production and pure quality raw water sources, and that's what I mentioned in the Netherlands. It's not uncommon. They actually have advanced oxidation processes in their water, normal water treatment. They're now putting in membrane systems increasingly in normal water treatment, and we have it in Australia as well. I know the Water Corporation in Western Australia, they use membrane systems on some of their smaller plants already as well. So it's not unusual to use these. The key point is also we can use it for production of very high quality industrial water. The very first water recycling plant in Brisbane was actually built for the refinery, and they actually wanted the very high quality water, and they were prepared to pay a premium for that over the not so good quality, not so pure, I would say, drinking water that was being supplied from council. I mean, there's nothing wrong with the drinking water, but they want high purity water for the boil makeup and for other operations in the refinery. The recycled water was actually a higher quality and needed for their purposes. But also food and beverage industry starting to use it, and I'll give you an example in a minute. Computer chip production. One of the reasons Singapore for a long time only had a few % of their recycled water going actually back into the reservoir was simply because the industry, particularly computer chip manufacturing, they were just taking that, and they wanted that water rather than the raw water, and so they were actually taking as much as they could, and only a few % actually initially went into the reservoirs. In the meantime, they have more capacity and there's more going there. And then the last one is industrial water recycling processes, and that's actually an example where these things have been going on for quite a while. This is an example, well, this is probably one of the first full-scale and very sophisticated integrated water recycling system in industry. That's the CUB brewery in Yatala, just between Brisbane and the Gold Coast. And they put this system in about 6-7 years ago, before the drought really hit. And it was already dry, but it was certainly not the driver behind it. I'll show you what the driver was in a minute. They already had anaerobic treatment, and they get the biogas from that, and they get obviously a good treatment from that. Then they had a number of additional steps put in, some biological, some filtration, then the microfiltration, then the RO, then an advanced oxidation process, which they added recently as well. And then they go to a storage tank from which they directly go back to the factory. So they're going directly back into the process stream. They're not making beer from it, simply because the beer water train is actually a separate one. The brewing water is always separate in the brewery from the process stream, but all of the process stream is actually largely supplied from that recycled water. And they've been doing this for many years. They get a lot of benefits, apart from the ones I'll show you in a minute, in terms of the water quality, a lot less scaling, a lot less cleaning chemicals needed, and so on in the actual process. The reason why they did this is that they put up a case to the board and got it approved simply on economic grounds. Now these numbers are a bit updated, because when they did it, the numbers didn't look as great as they do now. But what they're doing is they're saving around $3 a cubic meter for freshwater intake. They're saving another $3 or thereabout dollars for trade waste discharge costs per cubic meter, their operating cost for their whole system is less than $1. Do the sums. I mean, you have somewhere around $4 or $5 per cubic meter to pay back your capital cost. And even when they put it in, the numbers probably were about half of what they are now. Even then, it's stacked up economically. So they can do that purely on an economic basis. And they've been certainly not looking back since. During the drought, everyone had to cut back water consumption. They were actually happily already recycling their water. So there's plenty of these systems around. It's not the only one. Forex Brewery in town has also built one, very similar to this one. There is a chicken abattoir in Brisbane that actually uses that in their whole process as well. So they're actually doing it already. And that's really direct reuse. I mean, we're not talking even an environmental buffer. I mean, the only buffer you have there was the tanks you saw, and that's day supply. That's really just a buffer supply demand type thing. Why are they used? Again, because they're very good quality water, consistently good. Economics, as I just showed, is quite clear, and increasingly so. I think industry is going to move that way. Climate independent water supply augmentation, that's obviously the classic reason why we do it in the domestic side, but also protection for extreme events. And I'm saying droughts and floods. And the reason I'm saying floods is that this is a very famous scheme, obviously, up in Brisbane. This was built in response to the drought. This is part of the whole water recycling system, with the intention to actually then eventually discharge it into Ivanhoe. That's only once the dam is down to 40%, which is not going to happen for the next 5 years at least, even if it doesn't rain. So that's not running, but it's actually there. Now the reason that is not being used at the moment is partly because of that 40%, but to some degree you argue, why would you put it into the dam and the dam is overflowing anyway? What we could have done, in fact, while the dam was overflowing in the last floods in 2011 and in 2013, and particularly the 2013, the early January one this year, they had a big problem because the water quality was so poor at Mount Crosby, which is this little place just next there, which is the major water supply for the whole region. It's around about half of the water supply for all of southeast Queensland comes from that one plant. Water quality being so bad, they couldn't actually run the plant for about a number of hours anyway. And that just almost made the situation so bad that we almost ran out of water in Brisbane. They ran the desal plant flat out, which is another interesting thing because there was a flood. It wasn't a drought that actually made the desal plant come to full operation. And again, it happened in 2011 in the flood as well. But they could not use this recycling scheme because the dam was overflowing anyway. In fact, they wanted not more water up there, rather less. But what they could have done, had they one little connection, they could have actually recycled it back to the actual water supply side. So the direct option would have been a case to make use of very substantial multi-billion-dollar infrastructure that's actually there, which at the moment is pretty much not used and not usable unless the dam drops to 40% in the current political climate. But the direct option would have been feasible to actually help supply the city with water. What quality we can achieve? Well, I think we're pretty clear that it's extremely high quality. It's the same as desalination in many ways. And when you think of how we pull salt out of seawater, it's pretty impressive. The removal of chemicals, metals is not really a consideration anymore. You also get other benefits like very low organics, which limits disinfection byproducts, regrowth, extremely high potential for pathogen removal. And that's a point that's maybe sometimes a bit overlooked. And illustration of pathogen removal, I always say, oh yeah, we get 3 log reduction on this stage and 3 log on that one, and overall we get 9 log reduction. Well, what does it mean, 9 log? I mean, yeah, it's 10 to the 9, but what does that mean? So I tried to do a bit of a purely hypothetical study. Surface water supply system of 100 megalitres a day, that's sort of maybe 400, 500,000 people supply. We assume we have 0 viruses in that water supply, which is a bit brave assumption, I know, but it's irrelevant. We have a secondary treated effluent with about 10 to the 4 viruses per litre. We have a advanced water treatment process with a 9 log virus removal, which is actually realistic. that can supply half of that water, say, of the 100 megaliter. And we also have a secondary discharge that's just in the water supply. It's a very small one, 0.1 megaliter a day. That's like 500 people, 400 people, somewhere in a little village in the catchment, that also has a secondary treated, well-running wastewater treatment plant, discharges to the water supply line. What does it mean for a number of scenarios? So for the normal situation, we use the surface water and we have that little discharge. We end up with just these numbers are relative, not really absolute values, 10 viruses per liter at the intake of the water treatment plant. Obviously, the water treatment plant will then deal with that. If we now use, instead of having the recycled water, the secondary effluent going in, if we have the recycled water going in, we end up with, well, 5 millionth of a virus. So 5 viruses in a million liters, basically, at the water, out of that water. So that's what it means, 9 log reduction. If we now add that little wastewater treatment plant back into the process, that's how the number looks like, okay? So we're now changed from 10 to 10.00005 viruses per liter. That's what it means. I mean, that's what we've got to be realistic. If we now say, oh, well, but sometimes these treatment plants may not work and the AWT could be compromised. So we lose a whole 3 log reduction, which is massive and barely possible actually given the control and everything. That's how the number looks like. Okay, I mean, we've got to be realistic. I'm not saying these are right or wrong, it's whatever. They're just illustrations of what actually these things mean. So basically, why is it very safe? I think there is a number of different steps, independently acting, different type of treatments, high level of real-time monitoring, automatic control, is far exceeding what is usually done in water treatment plants. And I think the key point here is the real-time, because the real-time monitoring allows to actually measure at any one time directly online what is being done in every step. Not everything is perfect, and sometimes you can't measure the actual pollutant, but you measure some indirect measures, but at least it's real time, and whenever there's a problem, you can actually stop it. And that's one of the other points there, the third one. If there is a problem, you can allow the thing to stop, doesn't need to produce it. The water treatment plant in Mount Crosby in Brisbane, as we saw earlier this year, has about 24 hours to supply left when they stop producing. So you can imagine the pressure they were on in January to get that plant going again, even though there was still crappy water coming down the river, because there is just no option of running out of water. This thing you're really looking as an add-on. You can turn that off a week, a month if need be, until you know you have fixed the problem and you're sure you can actually supply the good quality water. So you haven't got that sort of pressure there. And ultimately it's been consistently demonstrated to meet all of the very stringent guidelines which have been in place. So really, I think it's a proven and existing proven technology. It's not really an experiment we're doing. It offers some valuable benefits, and Stuart's point is very valid, certainly a number of the cases he's made, and it's probably the safest and highest quality water economically achievable at the moment. So I'll leave it up at that. Thanks.